Good morning, everyone. My name is Muneera Shaibah. I'll be presenting today our work titled as the characterization of a resonant Lorentz force Muse magnetometer. This work was conducted at Khalifa University in United Arab Emirates, and it's also sponsored and funded by the UAE Space Agency as well. So this is a brief outline of what today's presentation is going to contain. Starting off with the introduction. So, magnetometer. A magnetometer is a sensor or device that measures the surrounding magnetic field intensity and direction. And such measurement is used for a wide range of applications, including aerospace, civilian, and geophysics, for various of reasons, mainly in navigation and detection of metal and geological structures, as well as to conduct some surveys. Now, magnetometers have been in the market for a few decades already. The traditional magnetometers have achieved high sensitivity and resolution, as small as femtotesla in the femtotesla range, and such resolution is considered relatively high or significantly high to be specific, especially since the Earth's magnetic field at the surface only ranges between 25 to 65 macrotesla. So that is a very high performance presented by these traditional magnetometer. However, they tend to be bulky and sometimes expensive or even complex to operate, which kind of add a bit more of disadvantages to these traditional magnetometers. An example of such magnetometer would be a flux gate magnetometer. Flux gate magnetometer utilizes a metal core in form of a ring or a rod to generate the necessary and drive this device, as well as sense and measure the intensity of the magnetic field. Now here we have in this table some examples of commercially available flux gate magnetometer. So as you can see from these values that the sensitivity of these devices are relatively high and they have very high performance. However, moving on to the dimension and mass, you can see that they occupy a large volume and tend to be on the higher mass scale, where this example over here in this image, the FGE flux gate magnetometer, for example, is reported to have the electronics weight to be only at 3 kilograms. And with the full integration of the system, they can reach as much as 20 kilograms. So it's very large, and which restricts the fields or the applications where it can be implemented at. Hence came the need for MEMS magnetometer. As the name suggests, it utilizes the MEMS technology, which produces structures in the micro scale, allowing to have a compact size magnetometer that can be virtually and almost implemented in everything or in almost everything that's needed, and especially in applications and fields that prior traditional magnetometers, due to their size and mass, were unable to be implemented. An example of these applications would be the mobile phones or the GPS on many devices, as well as the space explorations, especially in the CubeSat, which is the nanosatellite class, where there is a very large restriction on mass and volume. Aside from that, it offers low power consumption and as well as reduced cost. There are already several commercial MEMS magnetometer available. Here we offer you some two examples of such. These commercial magnetometers also found to have a relatively or actually significantly high resolution, as much as 8 nanotesla. Now, if you think about it, on the Earth's surface, the magnetic field is in the microscale, whereas if you go to in the LEO orbit, which is about 500 to 600 kilometers away from the surface, it's in the hundreds of nanotesla. So such resolution actually is very suitable for that application, especially in space. And not to mention the mass, the low mass provided by these new products. Aside from that, there are already also existing academic work which introduces several MEMS magnetometer designs, and they evaluated their performance. An example of that would be Thomson and Horsley, and their design found to have a resolution of around 1 microtesla with a quality factor of 48.8. So in our work, we're utilizing the Lorentz force principle. The Lorentz force is an electromagnetic driving force which employs the driving current along with the surrounding magnetic field to generate the necessary force. Using this principle eliminates the need to use magnetic material, which imposes a lot of advantages. One is it makes it suitable to be integrated with standard IC technology, as well as that the device will not suffer from hysteresis. Also, that it makes it easier to integrate with other MEMS sensors such as gyroscope and accelerometers. However, the absence of the magnetic material have a setback, which is that the device would require a drive circuit to generate the necessary current. As for the sensing technology, we're using capacitive sensing, in which the electrostatic field between the two electrodes or the two sensing element is disturbed due to the mechanical motion from the oscillation of the MEMS structure from the Lorentz force, the generated Lorentz force. Now, such disturbance is measured in terms of differential capacitance. Unlike other piezoresistive means, which although offers you relatively higher sensitivity, it generates a much less noise, as well as that capacitive sensing is widely used in other IMUs, inertial mass units, which once again makes it easier to integrate with other MEMS devices. Now, the gap changing capacitors, although it's common and has slightly higher sensitivity, it disallows or does not provide as much mechanical flexibility to the structure, restricting the movement of the device, which the area overlap capacitor design has, and it's used in the presented design. So moving on to the device and design specification. So you can see here in the right upper corner, we have the presented design. It is a single axis translational magnetometer. The main components can be categorized into two main groups. The first one is current carrying elements, also known as the driving elements, in which the driving current will pass through them to drive the structure. And these elements are the beams at the two ends of the structure, as well as the proof mass in the center of it. The second category is the sensing elements, at which the differential capacitance will be sent. And in our design, it is the COM fingers. We have two sets of COMs made of stator and rotor COMs, in which the two rotors are actually connected together through the proof mass. As for the Lorentz force, since the differential capacitance actually relies on the displacement of the COMs, the larger the displacement, the better. And to ensure that such large displacement occurs, the current is modulated at the resonance frequency of the structures to maximize the displacement. Hence, the Lorentz force expression becomes a function of the beam length, current, magnetic field, and as well as resonance frequency. The figure on the right illustrates the schematic of how the Lorentz force is being applied and where the differential capacitance is measured. This work is actually a continuation from last year's work that we submitted to the conference. In it, we presented a previous version of our device and conducted some basic analysis in order to and varied some parameters in order to improve the mechanical sensitivity of the device. And these were these two parameters were mainly the beam length and the beam width. And as you can see from the image, you can notice right away that the beam length were significantly shorter than the current one we have. We actually increased the beam length by around 115 micrometer, as well as the beam width was reduced by more than 50%. Below you can see some results obtained from last year's study. Moving on to the fabrication, the device was fabricated using MEMSCAP silicon and insulation foundry process. It consists of 4 layers: a substrate layer followed by an oxide layer which acts as an insulator, and then the third layer is a structural layer made of 25 micron thick silicon layer where all the main components are fabricated, and lastly it is topped off with a metal layer where the electrical bondings are being made. On the right, you can see the SEM image of the final fabricated device, and upon closer inspection, we found that the tolerances were in great accordance, and we determined that the quality of fabrication is of a high quality. Moving on to the simulation. So through Coventor MEMS Plus software, we were able to conduct some basic and simple simulation on the device, on the 3D model of the device. With a regular DC sweep, we were able to find the static capacitance, and it was reported 1.46 picofarad. As for the resonance, we conducted a model analysis on the structure. As mentioned earlier, we will be modulating the current in order to maximize the response, hence the need to find that value. However, the device has several modes, therefore the mode that exhibits the intended motion was selected, and it was found to be at 43.15 kilohertz, and luckily it was in the first mode, meaning that the device will not be overpowered by other modes. So a little bit of a comparison between last year's results and this year. As for the static capacitance, there was actually a decrease in value by 0.26 picofarad, and that's mainly due to the changes in the gap between the fingers, where they were increased by around 2 micron. As for the resonance frequency, it went significantly lower than last year, and that's again mainly because of the reduced stiffness and the increase in the flexibility of the structure, which was studied last year in the optimization process by changing the beam length and the beam width. Moving on to the characterization. The fabricated device was wire bonded to 24-pin DTIP package, and using the impedance analyzer, 2 terminals, we connected the low potential to stator and high potential to rotor. And by setting up the DC voltage, sweep, and the AC signal amplitude and frequency, the test was conducted at ambient conditions. Upon triggering the test, we obtained the following test result. You can see on the right, the test results obtained. The device was found to have a static capacitance of 1.276 picofarad, which is around 0.188 picofarad difference from the simulation, leaving us with a 14.7% discrepancy. As for the resonance frequency, we used a combination of a network analyzer with a DC power source to provide the rotor with an AC volt, whereas the stator was provided with a DC volt. The test was conducted inside a vacuum chamber at a pressure of 11.7 11.7 Pascal. Once again, upon triggering the test result, we obtained the following graph, or the following output. We saw and observed a clear peak with a 90-degree phase change at around 35.4 kilohertz. Now this test was repeated multiple times on the same device, as well as on other chips of the same device, and throughout all trials we got consistent results. Hence we are quite confident with this value, not to mention that we tested also the integrity of the test, and it was positive. Now this test result has about 7 kilohertz difference from the simulation, leaving us with a 20% discrepancy. Moving on to conclusion. So a single axis MEMS magnetometer that utilizes Lorentz force was presented to you. We have simulation and characterization results for static capacitance and resonance frequency. The fabricated device was found to have 1.276 picofarad static capacitance with a 35.4 kilohertz resonance frequency with a distinct phase change. For the static capacitance, there was less than 0.2 picofarad absolute difference with the simulation result, and there are several causes that may have led to such difference. The slight structural difference between the 3D model and the fabricated device in the sensing elements may have caused this, as well as parasitic capacitance from the wires and the wire bonding could have led to this difference, which we try to keep as minimal as possible and short as possible to reduce that effect. Lastly would be the sensitivity of the test to the human proximity. During the test, we found that as the user body would go near the test stand or test props, there was fluctuations in the readings from the test. Hence, this could have affected the overall output of the results. As for the resonance frequency, there was approximately 7 kilohertz difference. This may have been due to the structural difference between the 3D model and the fabricated device once again, as well as measurements error from the machines and the setup. Currently, we are building a drive circuit along with an evaluation circuit to amplify and convert the signal into a voltage output. This circuit will be used to conduct sensitivity characterizations on the fabricated device in order to evaluate their performance and determine it. As mentioned at the beginning of this presentation, this work is sponsored and funded by the Space Agency of the United Arab Emirates. Here are the references used in this research. Thank you for listening. Feel free to ask if you have any questions.